Evening, students. So it's already 7:08 and I think we should start this session. So, I welcome you all to this live session 12 on 15th of October 2022 for the course Physics of Renewable Energy Systems. So, this course is taught by Professor Amrish Chandra. He's from Department of Physics, IIT Kharagpur, and this live session is conducted by Rohit. I'm a research scholar at IIT Bombay. Think let's start this session. Anybody joining late, I will add them. See if anybody. Okay, so I have planned this session in which first we will do recap of this previous live session which happened on 8th of October. Then we will talk about the old assignment questions, different assignment questions from the previous run of this course. We'll talk about some concepts also, and I will added some beautiful slides on how the results of same or other things are actually represented. So you will get an idea also that how these instruments actually work. And I will also try to explain in a brief manner to interpret the results of these instruments or devices. And in the last, we will have question and answer session. Since this is live session 12 for week 12 course material, so most probably this will be the last live session of this course, or else there will be one more live session on the next week. So if you have any question related to exam or anything, you can ask in this live session, or else if you have any other doubts, you are always welcome to post that on discussion forum. So once again, welcome you all, and let's start this session. So if you see in the previous live session, we talked about different uh, spectroscopy, like different we utilize X-ray, UV, infrareds for spectroscopy, and we talked about FTIR, X-rays, all these things. So the most important, or I say very frequently utilized, is FTIR. So FTIR, what is FTIR spectroscopy? The name itself contains Fourier transform of infrared. IR portion here is IR here is infrared. So what does it do? It actually sends infrared spectrum and try to sense the light emitted from the or emissions absorption of the material, and it actually can be applied for all of solid, liquid and gas. And if you see, mostly FTIR are generally used for identifying the functional groups in the material or in the sample. So first thing is that sample preparation. You have to prepare sample with the exact directions. Then you conduct FTIR. You obtain results. The main important part is interpretation of these results. That is the main part. You can conduct FTIR, but you need to gain some specific insights and skills to actually interpret the results of FTIR. So also the spectrum which is for FTIR is generally between 4000 and 400 centimeter inverse. Okay, so this is the spectrum range. So if there is any question in the exam, what is the spectrum range for FTIR? So generally they ask these type of questions. So you must remember or note it down. It's between 4000 to 400 centimeter inverse. The second thing about the spectroscopy is Bragg's law. So this actually is the Bragg's law. N lambda equal to 2d sine theta. So what does it say? If there are two interplanar surface with distance d in between them, and some rays is actually striking it with angle theta and getting scattered with some angle theta or phi, anything you can say. So this wavelength, the wavelength of this striking ray can be represented in the form of n lambda equal to 2d sine theta. So how does this term come? You divide it here, connect it here. This will also be this is theta. So this is theta. That's how you interpret this result actually. N lambda equal to 2d sine theta. So this is actually Bragg's law. This is the main basic principle that is applied in spectroscopy, especially the X-ray spectroscopy. And third is we talked about X-rays. So X-ray can have a wide range of application. It is also used in medical field for identifying the fractures, cracks, etc. in bones. So the same thing. See, we have tears, cracks, fractures in atomic structure, atomic level, subatomic levels, etc. So that can easily be detected with the help of X-rays. So this comes under non-destructive testing methods actually. So X-ray, it generally affects the. There has to be a photographic plate which records the observation of the X-rays, and that photographic plate actually produces a latent image which has to be developed chemically. So that's how we obtain the X-ray. Also, these days what we see, some softwares are also there which record the X-rays, like the results of X-ray digitally. So we have digital X-rays also. Now the technology had advanced. Earlier, it had to be developed on a photographic plate. Okay, so there has to be some image on the photographic plate, and you must have seen some black color X-ray. That is the photographic plate which we use for X-ray development. Okay, and the third one was like a question, a conceptual question. How much is the? So I've just noted it down. This may be asked in the exam also, so you must know it. How much is the line broadening in X-ray peaks? Okay, you know the peaks. This is how the peaks are obtained. And this and these are peaks. Okay, these are peaks. So how much is the line broadening in the X-ray peak due to a strain effect and crystallite size? Okay. So remember, for strain effect, the line broadening is 4 epsilon tan theta, and from crystallite size, it's 0.9 lambda t cos theta. Now, I've just put two results. This is FTIR actually. This is FTIR. This is, I think, UV, FTIR or UV, similar type of thing. Okay, so this is actually a spectroscopy result of some grain growth, and it is showing grain growth with increasing temperature. So if we see the uh, result, you have to interpret what does this mean actually. So you see that the peaks, the first inference which we uh, got it from here is that the peaks height is actually increasing as we move forward. So as we move forward, what we are doing, we are increasing the temperature. So that's how you can say that as the temperature is increased, the peaks are actually increasing in height. Okay, so what does these peaks actually show? These peaks actually show grain growth. And the another thing is that there was no peak here, but as the temperature is increased, a peak, the first time it is seen as a peak in 700 degrees Celsius, then it grows and grows and grows. So you can say that at 700 degrees Celsius, new peak growth is actually identified. Okay, the figure on the right hand side is actually a result from FTIR. It's from a sample, or they have named it EPR S1B sample. Okay, So what did it see? So one side is transmittance, another is wave number. So this wave number is very much important. And the FTIR results, you see the FTIR results, you see that there are peaks. These are called peaks. Okay, and these are crest. These are peaks. You identify these peaks and note down the wave number from here. So each wave number is actually a representative of a or characteristic of a particular functional group only. So from these wave numbers we can identify and tell that these functional groups are actually present in the sample. Okay, so by identifying these functional groups, you can actually know what are the functional groups which are present in the sample. So this can come very handy, and uh, I can say not very handy, but it can give a good insights into what are the different characteristics or of the sample, what is there in the sample. So this can also be used for identifying adulteration, like you mix something in the uh, sample itself. So this will give a peak here if you add some potassium here in this sample. Okay, so you will get to know that at which wave number this potassium. So you will see a peak if it is the potassium source peak at 2500. So you will see a peak here. So you can identify that at 2500 I am getting a peak. So that means if potassium is there in this sample which need not to be present. So that's how you can say that the sample is adulterated. Okay, so this is also one of the use of this FTIR, and these instrument techniques are very advanced and they require a lot of skills for the experimentation, also for the interpretation of results also. So that's what is very important when you are using spectroscopy. Okay, so these are the important things which you need to keep in mind when you talk or study spectroscopy. Okay, let me see if anyone. Okay, so okay, so I think the concept is very much clear, and most of you must have identified or get a good idea about how these things are actually done. Moving to the next slide. So first question is, this is a question I have taken from previous run of the assignment. So the first question here says that zeta potential of a particle depends on. So when you talk of zeta potential, so this is a term which you need to focus. You need to know what is the zeta potential. Okay? So zeta potential, when you talk about zeta potential, so it has the term potential. So you know what is potential. The one thing can be potential energy. Okay, that we study, but this is not potential. Potential is generally voltage. Okay, which we get in this electrical terms. So this zeta potential actually in the broad sense or in a specific sense tells us about the potential difference. So what is this zeta potential? Why is this used for? So zeta potential is actually used to investigate collide electrolyte interactions. So I will tell you more about this zeta potential thing so that you get a fair idea of this. And this is very much utilized at a lot of places, zeta potential. Zeta potential, one example I can cite is membranes, the water filtration membranes. So when they make new membranes, they test a lot on this zeta potential, how it is behaving when the water is flowing, all these things. Okay, so what happens if you have a electrolyte and there are some colloids on it, but the electrolyte forms a layer on it, on the colloids or electrodes or something. So this actually measures the difference, potential difference between these two, the dispersion medium, which is electrolyte, and this stationary layer of dispersion medium attached to the dispersed particle. So if this is uh, say electrode and it has a deposition of this stationary layer of dispersion medium, which is this electrolyte, so it measures the potential difference between these two. That's what it is written here. What is zeta potential? So zeta potential is the potential difference C. It is saying about potential difference. Okay, so potential, potential difference. It is the kind of electromotive force or the difference of potential between the two electrodes, or kind of you say electromotive force that force the electrons to flow in a channel. Okay, flow through wires or something. So zeta potential is the potential difference between the mobile dispersion medium, that is electrolyte here, and the stationary layer of dispersion medium, that is electrolyte deposited on the head to the dispersed particle. So what is dispersed? This is. So we measure. That's a. I think it's very much used. Zeta potential is also used in biological experiments also. Like they measure bacteria or something uh, growth or something, theta potential, or they're correlated with some living organism. I am not very much sure about it, but I've seen some experiments regarding this in IIT Bombay. Okay, so now we have a good idea of what zeta potential is. So now the question. Now let us go back to the question. Question says that zeta potential of a particle depends on the first thing that you come to mind. If you are using electrolyte, so there must be pH of the electrolyte. It must depends on the pH. Second thing is measurement time. It doesn't have any effect on the measurement time. Why? Because if there is dispersion of the layer, so it doesn't have much effect on the C measurement time. The third is temperature of the solution, because as the temperature of the solution will grow, this dispersion and this medium will have change in this potential. So that's why potential difference can differ. Gives free energy, a totally different thing, that is actually related to batteries. And so only thing that actually this zeta potential depends is pH of the solution and temperature of the solution, that is A and C. Now the question 2. So question 2 is a very big question, and I would surely suggest you guys to note it down, this question, and try to solve it as I process through it. Then I will take this question after 5 or 10 minutes, so you can also practice it on your own. Take this first, have a look at this question. It's a very easy but a very conceptual question. Okay, so take a look. I will read this question for you. A metallic surface, when illuminated with light of wavelength lambda, emits electron with maximum energy value E. Okay, E is the emits electron with the maximum energy value E when it is illuminated with light of wavelength 2. Okay, so there is some mistake. So there is a wavelength 1, lambda 1, and there is a wavelength lambda 2. Okay, so two different lights which have different wavelength, and it emits electron with energy up to maximum level of, okay, this is E1, this is E2. So values of Planck's constant H, what should be the value of H, and work function of the metal can be expressed as work, let us say work function. Okay, so you got to know you have two rays, one is lambda 1, another one is lambda 2. So when it strikes a metal having work function W0, the maximum energy for this lambda 1 is E1, for this lambda 2 is E2. So it is saying that use these values and derive a relation for Planck's constant H. You know Planck's constant? So derive this value for Planck's constant H and the work function of this matter W0. Okay, so go through this question, try to solve it, and these are the different options. It's a quite easy question. It just looks big, but quite easy. So I will also try to solve it uh, after 5 or 10 minutes, so that you get ample time to try on your own. That's what I want. You try it yourself. So I have written a representation also here. E1 is this, E2 is this, 1 lambda 1. So you can use these values to get values of Planck's constant H and work function W. Now we move to the question number 3, that is scanning electron microscopy can be used in. So the first thing which you have to know is scanning electron microscopy. So what is scanning electron microscopy? There is a lot of microscopy, and within it, what is scanning electron microscopy? Okay, so check if any. So scanning electron microscopy is type or you say type of a device or instrument that is actually very much important to visualize a surface. It's a very important experiment on visualizing the surface. I will show the images also. So what it is basically scanning electron microscopy. Scanning electron microscopy, there is a term electron. It must be related to electron and electron beam. So what we do, we have a sample. Okay, we focus or bombard it with electron beams. So make sure that these beams which I am talking about are collimated, not in scattered or dispersed thing. Okay, so electron beam is focused on the sample surface by a set of lenses. So how do we focus it? The set of lenses, a collimating lens we say it focuses the electron beam on the sample, and the beams are actually parallel. So it is focused on the sample surface by a set of lenses in the electron column. There is a column in which this ray is actually okay. So there is some scattering here and there. Okay. So what there is a majorly three type of scattering is there in electron microscopy that we study. So one is back scattered electron. You see the electron beam is coming there and then it is getting scattered. These are back scattered. Okay, second one is secondary electron. Okay, some electron will be released from the surface, deep from the surface. uh, no, not deep. Secondary electrons are generally from the surface, not so deep. And third one is X-rays. So what does these actually tells us about backscattered electron scanning, secondary electron, and X-rays? So when we measure or see these backscattered electrons, so they give us images. They come from deep within the sample, and when I see deep within the sample in spectroscopic, especially the microscopy, scanning electron microscope, So don't assume it to be meter, centimeter, or these things. Okay, it is in range of few microns. So deep within the sample, so it is in the range of few microns. And what does it give? So it is coming from deep. So it gives compositional information. What is the composition of the sample, etc., etc. Okay. The secondary electron generally comes from topography of the surface, that is from the upper surface itself. So these are in some nanometers they cover. And what does they tell us about? It tell us about the topography of the surface. So what is topography? Topography are characteristic of the surface like undulations, the roughness, etc., etc. Okay, topography is a set of you say features of the surface. You can say whether it's rough, smooth. X-rays are actually measured. So we have a device attached to the SEM, scanning electron microscopy, called EDX, electric dispersive X-rays. Okay, so it actually measures these X-rays, and these actually tell us about the elemental composition. So that is very important. Third, I have also put image here. So for a better understanding, let's first solve this question. The question was, a scanning electron microscopy can be used in. So the first thing is it can be used for material science. Yeah, it can be used for material science. It can be used for forensic science. You know, forensic science, DNA fingerprinting, this you DNA fingerprinting, autopsy, etc., etc. Yeah, it can be used. Rock mineralogy, rock mineralogy is quite important. Carbon dating or these type of things. It actually not carbon dating. It actually studies the different composition in rock. So yeah, we can study the composition. What is rock made of? Rock mineralogy. Source is polymeric science, so it is also used for polymeric science. All these are actually correct. It is actually utilized for all these fours. So I put a image here also, so you can get a good understanding. So this is the sample. See the it is written here also sample. So this is the electron beam, focus electron. So these are the X-ray which are measured by EDX. Secondary electrons, we have backscatter electrons coming from deep. These are the things which are measured by scanning electron microscope. That's how it actually within inside the system it is this phenomenon that is actually utilized for this microscopy. So I have also taken some images from Thermo Fisher Instruments. So Thermo Fisher is a very good company that makes these instruments scientific. So you see EDX of this aluminum. This is EDX of copper. Okay, and this is SEM. Sorry, this is the EDX of this copper and aluminum. So that's what it is saying. The peaks and different composition. Below are the surfaces. I think this is for leaf of a plant. So that is how the leaf actually looks when it is put inside the EDX. Okay, these may be this chlorophyll pigments or something. Earlier it looked like this. When you zoom, looked like this. When you zoom further at 100 micrometer, it looked like this. You got, I think, must have got a good idea about how this electron scanning electron microscopy actually works. So I think we will do this question, then we'll go back to the numerical itself. We'll solve the numerical. Okay. I think that you guys must have been practicing that numerical. It's better you practice on yourself so that you develop confidence. So if these type of question are asked in the exam, you can easily answer. Which of the following is a required characteristic of an electron gun? Okay, electron gun emits electron. So if it's a gun emitting electrons, it must have high emission. This is correct. A small source size. This is also correct, because if you have a big source size, then there will be some difficulty in actually arranging or handling these things. Third is low energy spread. So you don't want this electron gun, you want it to be focused like this, okay, on the sample, not spread like this. So that's why it is also good. Low energy spread. We have where we have low energy spread in this. It is particularly focused. We have a high energy spread here. Beam stability. Okay, so if we are focusing a beam, it should be stable. It should not undulate like this. So all the four options are actually correct. I think question. So I think you guys must have understood this question. The question says a metallic surface when illuminated with light of wavelength lambda emits electron with one emits light of wavelength lambda 1 emits electron with maximum energy E1. When it is illuminated with light of wavelength lambda 2, it is emitted with maximum electron of maximum energy E2. So what is the relation between these things, E1, E2, lambda 1, lambda 2, and Planck's constant? And then what is the work function of the metal? Okay, let's see. First, if a light is striking a metal, so what should be a light of lambda? Okay, wavelength lambda. So what should be the energy? Sc upon lambda. Okay, and if this is the work function of the metal, and this is the maximum energy of the electron E. Okay, so what should be the difference between E1 and this light? So it must be W naught. Sc upon lambda, whatever is coming, so it must pass this work function of the metal plus the energy carried by the electron. So if we add these two, it will be equal to this energy balance, similar. So that is what written here. To write Sc upon lambda equal to E1 plus W naught. So if you rearrange it, putting it here, E1 equal to Sc upon lambda 1 minus W naught. So we have two rays, lambda 1 and 2. For these two rays, we write it like this. Now the main question is, we need the value of H. So that is important. We need the value of H. So what we do is we take lambda common, lambda 1 equal to Hc minus W naught lambda 1. So that's how this equation and this equation is obtained. So when you solve this question, these two equations, you eliminate the W. Okay. So how you can solve it? You just subtract this from this. Okay. So minus E1 equal to Hc remains common. It's 1 upon lambda 2 plus 1 upon lambda 1 and this W naught cancels out. Okay. Now if you want to obtain the value of H, what you will do? 2 minus E1. Okay. This will be lambda 2 into lambda 1 upon lambda 1 plus lambda 2 to C equal to value of H, Planck's constant. Let's see. You got it? Answer will be E2 minus E1 lambda 1 lambda 2 C lambda 1 minus lambda 2. Okay. 2 minus C1, 2 minus C1 lambda 1 lambda 2 lambda 1 lambda 2 lambda 1 minus lambda 2 into C. So must have got it. Now the second question. Second thing is that we put it here only so you guys could understand. For the second part, you need to know the work function. So HCSC is common here. Just subtract this from this. Okay, you subtract this from this. So what you will get? E2 lambda 2 minus E1 lambda 1 upon lambda 1 minus lambda 2. That is equal to what? E2 lambda 2 minus E1 lambda 1 minus lambda 2. Got it? This is the answer for W naught. This is the answer for H. So you can see, you just have to understand the question. That's all. If you, what is the concept here? The concept here is this: if a ray coming from with Hc upon lambda, there is a work function. So if you write a balance, an electron going out with energy E, so Hc upon lambda equal to work function that we need to cross out plus the energy contained in the electrodes. This was the concept. You utilize this concept to solve it and obtain these two values. Okay. I think this is done. This is done. Okay. Now the fifth question. Fifth question says the plot between real and imaginary parts. See the recording is running. Somebody wants to join. The plot between real and imaginary parts of the impedance of a supercapacitor cell in low frequency region would be. So have you seen the plot? This is like this y, iy, this is imaginary, this is x. So that's how the z is actually. You have seen typical impedance plotting. So it is like a linear figure. Okay. So the plot between real and imaginary parts of the impedance of a supercapacitor cell in low frequency region would be linear. Correct answer is A. This is just a conceptual question. You have to go through slides and you will get to know how are these plots. And can SEM produced colored images? Good question. Options are yes and no. So if you see SEM, scanning electron microscope, so it has backscattered electron, the secondary electron and the X-rays. So it doesn't have ability to produce colored images. When you go for colored images, you need to have different wavelength. So there doesn't have different. It has electrons, backscatter, secondary electrons, which are actually studied for this production of these images. So no, SEM cannot produce images. Images are always and always black and white only. So I have put this images here also of different thing. I think this is for cut section of some metal or a leaf. I put these images here so you guys could get a greater understanding how the images of SEM actually looks. So these are the different images for different types of samples of SEM. And you if you guys have actually seen SEM, or you go to any research laboratory where SEM is installed, you can put the sample preparation is quite a big thing. So the samples are actually prepared very carefully. There's a platinum sample holder. It's a very small, so we don't put a big sample there. We put sample 1 or 2 grams, or even less than that. Okay, so these are to be tucked in, then they are placed in the EDX or same EDX machine, and there is a associated computer screen where the software runs, and it actually produces images. It actually gives the results. That's how SEM is actually realized for producing the images. So you can see these are the different images, and these are very zoomed in images like 100 nanometer or some scale. Okay, you go zooming and zooming, you need to observe the different changes on the surface due to some process activity. So you can utilize SEM always. So the correct answer here is answer B. SEM cannot be for producing colored images. Now the question 7. So if you see the question 7, zeta potential can be defined as, it is saying that particle potential, Stern potential, surface potential, potential at the edge of diffuse layer. So when in the first slide when we talked about zeta potential, so there was electrolyte, there was electrode or dispersed medium. Dispersed medium is this electrolyte. The colloid or first phase is this, and there is a layer outside, and this is the potential difference that measures as zeta potential. So zeta potential is potential at the edge of the diffuse layer. The correct answer is answer D, not surface potential. It doesn't measure the surface potential. It is not the particle potential, neither it is the Stern potential. Okay. Now coming to the question 8. It's I would rate this question as a very simple question because it's just a formula based question. So yeah, expect these type of questions in the exam. We have these type of questions in the exam. So make sure you grab the formulas. You know how to use them. It's important not only to grab the formulas. You need to know how these formulas are actually utilized in getting the results. So what is the question? First, you need to understand the question. The question says a supercapacitor device. So it's a supercapacitor working within a stable potential window of 1.2 volt. So the potential window is 1.2 volt, can be discharged fully within 80 seconds. You got another time, discharging time, at a current density of 2 ampere per gram. Indicate the specific capacitance. So you know the specific capacitance per with respect to weight or mass. Okay, so that is specific capacitance. Value of the device, consider the voltage drop for the device at that particular current density to be 0.06 volt. So what is the relation of a specific capacitance with all these parameters? So you know specific capacitance is equal to I upon M dt upon V minus IR, where CS is specific capacitance, I is the current density, M is the stable potential window. Okay, no, it's not potential window. M I upon M is the current density. So it's ampere per gram. Okay, so I upon m is given here. If it is not given there, you are given I, you are given m, then put the values here. But you see, current density of 2 ampere per gram is given here. You directly put it here. dt, you know, the discharging time is 80 seconds. P is actually this stable potential window, 1.2 volt, and IR is current multiplied by resistance, which gives this voltage drop is IR. So you put the values. I upon m, you know, 2 into dt, you know, 80. 1.2 is the stable potential window, and minus IR is 0.06. Okay, calculate it down. It's calculated without calculator, so there won't, you won't be allowed to use calculator in the exam, so there will be on-screen calculator which you have to use. You can calculate it with the without the help of calculator also. It's very easy. You subtract this 1.14, I think this is 100. Okay, so we have 16,000 divided by 114. We get 114, get 44 here, 440, then we get 4, and then 0. So it will be something around 140 farads per gram. Why per gram? Because it is asking about a specific capacitance. So the answer is in farad per gram. So the correct answer is answer C. Okay. So this is the end of this live session of week 12. So we did some revision of the previous live session. Talked about FTIR results, identifying and interpretation of results, zeta potential, numericals, scanning electron microscopy, and electron guns. These things plot between real and imaginary. We also saw the different same images of different samples. Then we solved a question related to supercapacitor. Okay, so if there are any queries, you can ask the queries here. I'm here to answer your queries, or if you want to have a discussion, then you can put it on discussion forum also. So your queries will be answered there also. So if there are any specific queries, the more students can benefit from your answers, from your question actually. Also, if there are any query related to exam or something, you are allowed to ask here. I will try to clear your doubts. I think there are no queries. So exam, I think they have made announcement regarding exams. So try to go through the announcement. I think the exam is online type of exam. So you will have MCQ type questions. You will have essay type questions also writing. So try to practice all these things, and you will have numerical answer entry type questions also. Try to practice, and yeah, go through the slides. These are very comprehensive slides, and I am sure that you must have benefited from this course and the live sessions also, because we take your questions, we try to take the previous live assignments questions, so that you get an idea of what type of questions can be asked in the different stages also. Okay, and we also tried in the live session to take your doubts. So whatever doubts you have, it actually increases the interaction between this course content and the student which you are. So that's how it was planned, and I think I have had a very great experience teaching you guys. the different concepts, the assignments, and all those things. So even if you need any help regarding the course, you will always find me at this email address. Uh, Thank you all, guys. Thank you for the live session, attending this live session. If there is any other class in the next week, you will be informed through mail, and we will. Okay. So thank you all. Thank you again for the wonderful session.
And why aren't you in uniform?